Over the past decade, many countries in Southeast Asia have achieved great progress in the treatment of tannery effluent. Both individual and common effluent treatment plants have been set up by the tanners for this very purpose. In India itself, 16 common and more than 180 individual effluent treatment plants are currently operating in the tanning industry. These plants have been successful in treating effluent so as to meet, by and large, the pollution discharge norms prescribed by the Pollution Control Authority. Similar developments have taken place in Nepal, Indonesia, China and Pakistan. Bangladesh and Sri Lanka are also in the process of developing treatment facilities of this kind. In arid regions, however, especially in places where tannery effluent cannot be mixed with domestic sewage, total dissolved solids, or TDS for short, pose a major problem. Tamil Nadu in India is a case in point. Although most of the effluent treatment plants in the state produce treated effluent that conforms to discharge standards set for nearly all parameters, the effluent itself is virtually useless. In fact, it is positively harmful given all the dissolved solids it contains, for the most part chloride and sulfate. For discharge into surface water, the Tamil Nadu Pollution Control Board has set the discharge limits for TDS at 2100 milligrams per litre and for chlorides at 1000 milligrams per litre. In many instances, groundwater contaminated by effluent high in TDS is unfit for human consumption. In other instances, the rise in salinity in the soil has had a negative impact on fertility and agricultural productivity in this area. Local tanners, enforcement authorities and environmental specialists are thus eagerly looking for options that are technically and economically viable. Let us see how TDS gets into the tannery effluent in the first place. Two types of salts commonly found in tannery effluent are chlorides and sulfates. Chlorides mainly come from the common salt used to preserve raw hides and skins to prevent them from putrefying during the period that elapses between flaying and tanning. In many parts of India, this period ranges between 15 and 45 days. The quantity of salt applied is about 40% of the weight of raw material. Often, excessive amounts of salt are used. A significant amount of chlorides also emanate from pickling. Sulfates emanate from the use of sulfuric acid or products containing a lot of sodium sulfate. High levels of sulfates are to be found in chrome tanning salts as well as many syntans and auxiliary chemicals. Sulfate is also formed when sulfides oxidize in the effluent treatment plant during aeration. How and when do chlorides and sulfates enter the effluent streams? The first process inside the tannery involves washing the hides and skins and rehydrating the material by soaking it in water in a paddle or drum. During this soaking process, much of the salt applied dissolves, and the soaked liquor discharged contains the highest concentration of TDS during the whole tanning process, no less than 40,000 to 50,000 milligrams per litre. The other steps in the tanning process which contribute to TDS are liming, deliming, pickling, tanning and finishing. Residues of such chemicals as ammonium chloride and sulfate, sulfuric acid, chromium sulfate and some dyestuffs enter the effluent stream and add to the volume of total dissolved solids. The various options for the management of TDS include avoiding or reducing the use of common salt to preserve hides and skins, avoiding chemicals with a high salt content, for example, replacing ammonium chloride or sulfate deliming with carbon dioxide deliming, enforcing in-plant control measures to avoid excessive use and overdosing of chemicals, introducing appropriate end-of-pipe treatment, devising safe methods for the disposal, utilization of salt recovered from different solid and liquid waste streams. The use of preserving salt can be completely avoided if green hides are taken direct to processing from the slaughterhouse, thus avoiding the storage phase. If this is not feasible, the alternative methods that can be used are curing by drying, curing by chilling, curing with the use of selected antiseptics and biocides. Drying raw hides and skins removes the moisture and preserves the material. Different drying techniques are used, be it frame drying for hides or suspension dryings for skins. For various reasons, such as handling, grading, and transport considerations, traders and tanners have no particular liking for the dried raw material. Raw hides and skins can also be cured by cooling and chilling using ice or cold air. Storage at temperatures below 4 degrees centigrade is quite safe and guards against bacterial attack for about 20 days. The process, however, is energy intensive and may only be suitable where abattoirs, rawhide depots and tanneries are equipped with cold storage facility. Refrigerated containers are needed to transport the chilled stock. Usually, facilities of this kind are mainly available in industrialized countries. At the same time, and despite promotion by various suppliers and research establishments, the use of selected antiseptics and biocides has met with limited success. For the time being, the wet salting of hides and skins is still the most widely practiced technique throughout the world. It has the advantage of being simple, and salt is readily and cheaply available. Accordingly, in the foreseeable future, the TDS problem has to be tackled with this reality in mind. Under its Southeast Asia Regional Program, UNIDO has attempted to demonstrate on an industrial scale a basket of technological options for tackling the problem posed by TDS in tannery effluent, as there is no one-track solution to the problem. Removing the salt sticking to the hides and skins before they are soaked helps to reduce the TDS in the effluent. This first step is done manually or mechanically prior to soaking. To facilitate manual desalting, UNIDO has developed a wooden frame called dodeca. The hides and skins are beaten on it manually to remove the salt. This operation removes salt equivalent to about 7% on the weight of raw stock. For larger tanneries, a drum, even an old unused tanning drum with suitable internal modifications, can be used for mechanical desalting. This is particularly suitable for large hides. It is estimated that this operation removes salt equivalent to 5% on the weight of raw stock. Another mechanical means of salt removal is a brushing machine. Hides and skins are passed through 2 rollers with brushes. This too helps to remove salt to the extent of 7% on the weight of raw stock. The salt collected from these desalting processes can be dissolved in water. The impurities in it are precipitated using a simple chemical process, and the saline liquor so obtained is then reused in the pickling process. The salt recovered is also collected by traders in hides and skins who use it to preserve raw material in transit. This is not really recommended as the salt may contain impurities. The desalting process can reduce the total dissolved solids in effluent by some 20 to 30%. It also offers the option of the salt being reused by tannery. The UNIDO regional office in Chennai has published a technical manual that provides more details on options for desalting and the reuse or disposal of salt. The next stage in the tanning process is the soaking operation. Soaking involves 2 or 3 washes. Counter-current soaking is a process which entails using spent water from the second wash in the first washing, and the spent water from the third wash being reused in the second washing. This can reduce the amount of water consumed during soaking by about 40 to 50%. This in turn helps to reduce the hydraulic load of the effluent from the soaking section. Ultimately, it helps to reduce the pond area required for solar evaporation. Depending on the specific circumstances, spent floats contain large quantities of unabsorbed salt, acids and/or alkalis. Recycling and reusing spent floats yield a better uptake of unabsorbed matter. Consequently, the pollution load of the wastewater discharged is lower. Moreover, recycling and reusing floats reduce water consumption and thus the overall hydraulic load of the effluent. The most commonly used liming and unhairing system comprises 200 to 400% water, 2.5 to 5% hydrated lime, 1 to 3% sodium sulfide. When using the classical dosage of 3% liming and 3% sulfide, the unhairing liming process consumes only 40 to 45% of the lime and 50 to 55% of the sulfide. The rest remains in the spent liquor. Given the high concentration of residual lime and sulfide, the spent float can be directly recycled for the next batch. In addition to saving costs, this method reduces the discharge of pollutants, including TDS, in the wastewater streams. The first step entails recovering a maximum quantity of residual float. Drums, especially those fitted with modified doors and drain valves, permit recovery rates of the order of 70 to 75%. Paddles and vats cannot be drained effectively, yet some tanneries still use them for direct recycling. There, however, the recovery rate is generally lower, about 60%. The spent float passes via a separate stream to a collection sump where it is stored. It is then pumped through a fine screen. After screening, the liquor is held in a tank. Here, it is gently agitated to prevent the sulfide oxidizing any further. The liquor volume and the lime sulfide concentration are checked. Water, lime and sodium sulfide are added as required for the next batch. Under normal working conditions and over a period of 20 cycles, recycling spent float offers savings of the following order: water 40%, lime 45 to 50%, sodium sulfide 35 to 40%. Preventing the discharge of unutilized lime and sulfide into wastewater streams and recycling spent liquor have proven very effective. They have appreciably contained the generation of TDS in the beam house. The TDS in floats discharged after pickling can be reduced by simply limiting the float volume to 50 to 60%. This in turn reduces the quantity of sodium chloride used in pickling by 2 to 3% on the weight of the delimed pelts. Recycling pickle floats is already common practice in many tanneries. After being collected in one batch, the float is screened and its acidity and salinity determined in a laboratory. After adjustment to the requisite pH and salinity values, the float is then reused for pickling in the next batch. By recycling pickle floats in this way, about 80% of the salt can be saved and acid consumption can be reduced to 25%. Spent chrome liquors can be recycled in a variety of ways. Direct recycling reduces the use of both sodium chloride and chrome powder, which contains up to 30% sodium sulfate. The spent chrome liquor is collected, cooled and settled. After adding acid and a masking agent and adjusting the specific gravity with salt, the liquor is used in the subsequent pickle. The amount of salt required depends on recycling efficiency. It usually corresponds to 2% on hide weight. Direct recycling of spent chrome liquor can reduce the TDS load in the tan yard effluent from 65 grams per kilogram of rawhide processed to 7 grams per kilogram. Now that we have seen the different in-process control measures, let's take a look at what options are available at the end of the pipe. Effluent treatment also offers some scope for reducing TDS given effective measures. Replacing or reducing common chemicals with polyelectrolytes is one way of combating an increase in TDS during effluent treatment. According to the Pollution Control Authority, tanneries in Tamil Nadu have to segregate the soak and pickle liquor and discharge it into solar evaporation pans. There, the water is evaporated and the salt recovered in crystalline form. Large plots of land are required for such an operation. They are not so easily available, with the result that most solar evaporation pans are under-designed and improperly operated. The average evaporation rate in the tannery district of Vellore is 4.5 millimeters per day. The tanneries are thus required to produce 222 square meters of surface area per cubic meter of effluent discharged for solar evaporation. In those rare cases where the liquid is fully evaporated, the salt obtained is mixed with dirt and other impurities. Unless the salt is removed and disposed of safely or reused, segregation does not serve the intended purpose. The UNIDO project team and the staff from a tannery in Ambur, India, decided to join forces. They set up and tested an accelerated solar evaporation system. The Indian Institute of Technology in Chennai also collaborated. The system employs complex thermodynamic principles in a down-to-earth manner. The saline liquor is first purified by chemical precipitation, and the clear supernatant is fed into an inlet collection tank. The saline liquor is then pumped up to a channel on a platform, and from there it flows down over an inclined flat plate collector. When flowing down the plate, the liquor heats up and is collected in a tank below. It is then pumped back up again and sprinkled down through fine nozzles. The sprinkled liquor drops down into a collection tank below before being rechanneled to the flat plate collector. The alternating series of heating and sprinkling cycles increases the evaporation rate to 3 to 4 times the normal daily rate. The concentrated liquor from the system is then taken for conventional evaporation in the pans. It is there that the crystallized salt is recovered. In a medium-sized tannery, this improved solar evaporation system has successfully reduced the effective area required for solar evaporation by about 30%. What is more, the salt crystals recovered are much cleaner. They are reused in pickling in the tannery. However, on account of the various monitoring facilities set up and the safeguards provided, the cost of the improved solar evaporation system was on the high side. The operational cost of evaporating 1 cubic meter of saline effluent was found to be approximately $1.55. This has to be seen in relation to the estimated value of the salt recovered. It is of the order of some $0.76 per cubic meter, assuming a unit price of $0.023 per kilogram of salt recovered. The UNIDO team has, in cooperation with a private sector tannery, established a radically simplified design. The capital and operational costs have been reduced substantially. Apart from collection tank, chemical treatment unit, sand filter and the storage tank, the simplified design has only sprinkler units to sprinkle the clarified saline effluent. The operational cost for evaporating 1 cubic meter of saline effluent in the simplified version has been found to be $0.36. Good quality water can be recovered from the treated effluent containing high TDS. It entails adopting advanced membrane technologies such as reverse osmosis. This option is becoming increasingly relevant. Not only are TDS becoming more and more of a problem in many parts of the world, but membranes are also getting markedly cheaper. Moreover, in many instances, tanners are obliged to buy the water they need for the process. Economic imperatives are at play. UNIDO entered into cooperation with an isolated tannery that had its own effluent treatment plant. As part of the project, UNIDO installed a pilot unit for reverse osmosis to evaluate a process designed by a Chennai-based company, Aqua Chemicals and Systems Limited. The treated effluent is first polished in a pre-treatment system comprising sand, carbon filters and chemical dosing arrangements. It is then passed through a membrane. This is the first stage of the reverse osmosis process, in the course of which all the contaminants in the water are removed except for the salt. In the second stage of the process, the salt is removed from the water to produce pure water with TDS at less than 500 milligrams per litre. Water recovery in the unit is in the order of 70 to 75%, and the water so recovered is suitable for dye house applications. Rejects from the reverse osmosis unit are sent on for solar evaporation. Use of an improved solar evaporation system would improve evaporation efficiency. The UNIDO pilot unit has demonstrated the technical feasibility of using reverse osmosis to recover good quality water from saline effluent. However, the cost of so doing is rather high, more than $0.93 per cubic meter of effluent treated. This is considerably more than the current price for water supplied to the tannery. Moreover, it has not been possible to assess the working life of the membrane. The pilot demonstration ran for too short a period, scarcely 1.5 years. Based on the experience gained from the pilot plant, the Chennai-based Aqua Chemicals and Systems have offered to set up a similar project on build, own, operate and transfer BOOT basis. The proviso being that the price of the good quality water recovered would have to be fixed for a specific number of years in advance. The UNIDO team and the management of Common Effluent Treatment Plant at Ranipet, India, have conducted a series of experiments to see whether effluent containing a comparatively low level of TDS, especially chlorides, could be used to irrigate non-edible plants. They closely monitored both plant growth and the effect on the soil and groundwater. Every day over the past year, except during heavy rains, about 700 cubic meters of effluent containing between 4,000 and 5,000 milligrams per litre of TDS and 600 to 900 milligrams per litre of chloride have been used to irrigate an area of about 8 acres. More than 25,000 plants of different species have been grown on the plot. To date, no significant increase in TDS or chloride in the groundwater or soil has been observed. UNIDO continues to monitor the project. In summary, effective TDS management in the tanning industry calls for appropriate interventions in the following areas: elimination, total or partial, of the use of salt to preserve hides and skins. This can be done by processing fresh, green hides, curing by drying, curing by chilling. Reduction of TDS or the hydraulic load of effluent generated in process. This can be done by desalting salted raw stock, recycling soak float, recycling liming float, recycling spent pickle liquor, recycling spent chrome liquor direct. End of pipe treatment of TDS. This can be done by accelerated solar evaporation of saline effluent, desalination of saline effluent using membrane technology, use of treated effluent in irrigation. Tanners are adopting one or a combination of these options to combat the problem of TDS in the effluent. This holds particularly true for Tamil Nadu, India. UNIDO is continuing its efforts to enhance the technological options for dealing with TDS in effluent. A particular focus being lower investment and operational costs, as well as simple replicability. Technical papers and reports on all these subjects can be obtained from the UNIDO regional office at Chennai or from the UNIDO leather unit in Vienna.